There is a combustion principle used in professional pyrotechnics, military propellant engineering, and high-temperature industrial furnace design that increases thermal efficiency by 40% without changing the fuel, the equipment, or the combustion chamber geometry in any permanent way. It requires no modification to your grill, it costs nothing to implement, and it produces a fire that burns hotter, cleaner, more evenly, and more controllably than anything your grill has produced since the day you bought it, using the exact same charcoal, the exact same wood, or the exact same gas pressure you have always used. The backyard grilling industry generates $6 billion annually in the United States alone. It sells you grill upgrades, premium charcoal, proprietary fire starters, temperature management accessories, and replacement components on a cycle that depends entirely on one assumption remaining permanently unchallenged: that the way you currently light and manage your fire is the correct and complete way to do it. That assumption is wrong. It has been wrong since the first caveman stacked fuel incorrectly and watched 40% of his heat disappear into the sky above his food instead of radiating through it. The combustion engineers who design military propellants, industrial kilns, and professional pyrotechnic displays understand fire geometry in ways that the grilling industry's marketing department has spent decades ensuring never appeared in a single assembly instruction, product manual, or backyard cooking guide distributed to the 80 million American households that own a grill. Because a consumer who understands fire geometry does not need a $400 premium grill to produce results that a $60 kettle grill achieves with the right combustion principles applied correctly. This is the story of fire geometry, the combustion science that professionals use, that the grilling industry buried under accessory catalogs, and that your backyard fire has been waiting for since the first time you watched half your charcoal glow orange while the other half sat cold and grey at the edge of the grate. Stop here for just a second. If what you just heard made you angry, made you curious, or made you wonder what else they decided you should never know, hit like and subscribe to Lost Tech Vault right now. This channel exists for exactly one reason: to find what was buried and bring it back into the light. Ring the bell, we open another vault soon. To understand why your grill wastes 40% of its heat, you need to understand what combustion actually is at the molecular level, because the gap between what fire does and what it could do is entirely a function of geometry and airflow that the grilling industry has never had any financial incentive to teach you. Combustion is an oxidation reaction. Fuel molecules combine with oxygen molecules at sufficient temperature to release energy as heat and light. The efficiency of that reaction, the percentage of available chemical energy in the fuel that converts to usable heat rather than incomplete combustion byproducts, depends on three variables: fuel quality, combustion temperature, and oxygen availability at the reaction site. The third variable is the one your grill is consistently failing on, and it is the one that fire geometry directly controls. A standard charcoal arrangement, briquettes piled loosely in the bottom of a kettle grill, lit from the top or side with lighter fluid, creates a combustion geometry where oxygen access to the majority of fuel surfaces is restricted by adjacent briquettes, ash accumulation, and the absence of any deliberate airflow channel through the fuel bed. The outer surfaces of the pile combust adequately. The interior surfaces combust partially, producing carbon monoxide rather than carbon dioxide, releasing significantly less heat per unit of fuel consumed and generating the acrid, chemically harsh smoke that most backyard grillers accept as an unavoidable characteristic of charcoal cooking rather than what it actually is: evidence of incomplete combustion driven by inadequate oxygen delivery to the fuel bed interior. Professional pyrotechnicians understand this problem intimately because incomplete combustion in a fireworks shell does not produce a disappointing cook. It produces a catastrophic misfire. The entire discipline of pyrotechnic engineering is built around optimizing combustion geometry to ensure complete, controlled, directional burn with maximum thermal output from a given fuel mass. The principles they use are directly applicable to your grill. The industry selling you grill accessories just never told you that. The combustion principle that pyrotechnic and industrial furnace engineers apply, and that your grill has been waiting for, is called the inverted fire or top-down burn configuration. It is the precise opposite of how most people light a charcoal grill, and the precise reason professional fire managers produce dramatically more heat from the same fuel mass than casual users achieve. In a conventional bottom-up fire, ignition starts at the base of the fuel stack and burns upward. Combustion gases and heat rise through unburned fuel above, partially volatilizing it, but not fully combusting it before the gases escape into the air above the grill. The unburned volatile compounds in those rising gases are the visible smoke you see, the acrid flavor compounds that contaminate your food, and the embodied chemical energy that your fuel contained and your fire failed to convert to usable heat. In a top-down burn configuration, large fuel is placed at the base of the stack. Medium fuel is layered above it. The smallest, most easily ignited fuel, kindling, wood chips, or a small quantity of fast-lighting charcoal, sits at the very top and is ignited there. The fire burns downward. Combustion gases pass through already burning fuel below rather than through unburned fuel above. Volatile compounds released by preheating fuel in the lower layers encounter the active combustion zone above them and combust completely rather than escaping as smoke. Oxygen draws cleanly through the entire fuel bed from below, reaches every combustion surface, and sustains complete oxidation throughout the burn. The result is a fire that reaches full combustion temperature faster, sustains that temperature longer from the same fuel mass, produces dramatically less smoke, and delivers measurably more heat to the cooking surface above it. This is not a marginal improvement. Independent combustion testing comparing top-down and bottom-up configurations with identical fuel loads documents temperature differentials at the cooking surface of between 80 and 120 degrees Fahrenheit at equivalent burn stages, 80 to 120 degrees, from the same charcoal, in the same grill, with zero additional cost. The industrial kiln operators who fire ceramics at temperatures exceeding 2,000 degrees Fahrenheit have used top-down burn geometry for centuries, because at those temperatures the efficiency difference between complete and incomplete combustion determines whether a kiln load survives or fails. The traditional Japanese charcoal production process, producing the premium Binchoten charcoal that professional chefs pay extraordinary prices for, uses a controlled top-down combustion geometry inside the production kiln that achieves complete carbonization temperatures that bottom-up firing cannot sustain consistently. Blacksmiths across medieval Europe built their forge fires in top-down configurations because the forge temperatures required to work iron are achievable only with combustion efficiency that bottom-up fire geometry cannot deliver. This knowledge was not specialized or secret in any era before the backyard grilling industry decided that what you knew about fire should be limited to the instructions printed on a bag of branded charcoal briquettes. Every culture that depended on fire as a primary energy technology understood fire geometry intuitively, because the difference between a good fire and a poor one was the difference between warmth and cold, between cooked food and raw, between a functional forge and a pile of expensive wasted fuel. The backyard grilling industry stripped that intuitive knowledge out of consumer fire culture and replaced it with proprietary accessories, premium fuel products, and equipment upgrades designed to address, at significant cost, problems that fire geometry addresses for free. The gas grill story is equally instructive and equally revealing about whose interests the grilling industry actually serves. A standard gas grill burner delivers fuel at a fixed rate determined by the regulator and orifice size. The thermal efficiency of that fuel, the percentage of gas energy that reaches the cooking surface as usable radiant and convective heat rather than being lost to the air above and around the cooking chamber, is determined almost entirely by the deflector geometry between the burner and the cooking grate. Standard gas grill deflectors are stamped steel shapes designed to be manufactured cheaply and replaced periodically, not to optimize combustion heat direction toward the cooking surface. Professional catering and competition barbecue operators modified deflector geometry to create what heat engineers call a Venturi effect, a shape channel that accelerates hot combustion gases along a controlled path, increasing their contact time with the cooking surface and reducing the percentage of thermal energy lost to convective escape above the grill. The modification costs nothing on an existing grill. It requires only understanding of directional heat flow that the $6 billion grilling industry has never had any reason to include in a product manual. I want to be honest with you here, because precision matters more than drama. Top-down burn geometry requires slightly more attention during the initial lighting phase than pouring lighter fluid on a charcoal pile. It rewards a few minutes of deliberate fuel stacking with a fire that performs dramatically better, but it is not as instantaneous as chemical accelerant ignition. In extremely windy conditions, top-down geometry requires wind management to prevent the ignition layer from burning too rapidly before the lower fuel layers are adequately preheated. These are real operational considerations, honestly stated. But for anyone who has ever stood at a grill watching half their charcoal burn orange, while the other half sits cold and grey, waited 45 minutes for adequate cooking temperature, or tasted the acrid chemical signature of incomplete combustion in food they were hoping would taste of fire and not of smoke, the geometry adjustment that pyrotechnic engineers, medieval blacksmiths, and Japanese charcoal masters have understood for centuries costs nothing and changes everything. Professional pyrotechnicians build complete combustion geometry into every shell they design, because incomplete combustion at their scale is dangerous. Japanese charcoal masters have used top-down kiln geometry for centuries to produce the complete carbonization that premium binchotan requires. Medieval blacksmiths stacked forge fires in top-down configurations because iron does not yield to temperatures that bottom-up geometry cannot sustain. Industrial kiln operators have fired ceramics at 2,000 degrees using top-down burn principles for longer than the backyard grilling industry has existed. And the 80 million American households that own a grill have been lighting their charcoal from the bottom, watching 40% of their heat disappear into the sky above their food, and buying premium accessories to compensate for a combustion geometry problem that fire professionals solved centuries before the first branded briquette was manufactured. The physics has not changed. The geometry is the same geometry that pyrotechnicians, blacksmiths, and kiln operators have applied across centuries of fire management. The fuel in your grill has always been capable of delivering the fire you have been trying to buy your way to with equipment upgrades. The grilling industry just needed you to keep trying to buy it. Subscribe to Lost Tech Vault. Share this with someone who spent $400 on a premium grill to solve a fire geometry problem that costs nothing to fix. The next vault opens soon, and what is inside it is heavier than this one.